Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Welcome. This is Mr. Simon. Hope you are doing well, and we are here to change our world with chemistry. So today we are going to talk about our new topic, unit number 12, that is conductivity of solutions. And our lesson title is conductivity and conductance. Conductivity and conductance. So by the end of this lesson, students should be able to explain conductivity and conductance of solutions. So quickly, so when someone talks about conductivity, you actually get a simple meaning that we are dealing with electricity. Actually, conductivity is a branch of electricity. That is a branch of electrochemistry. And this electrochemistry deals with the transfer of electrons from one chemical species to another, and the relationship between electron transfer and electric current. So if you remember about electrolysis in senior 5, normally when we have an electrolyte, that is when electricity passes through an electrolyte, we have conduction of that electricity. So this time we are going to talk about conductivity. So before we talk about conductivity, let's talk about these two terms. We are going to talk about electrolytes and non-electrolytes. So who can define for us the term electrolyte? Electrolyte from senior 3 or from your O level. Actually, an electrolyte is a substance which conducts electricity in either aqueous or molten state. So because we are dealing with chemistry, we are going to basically be dealing with solutions. So meaning that when we are dealing with solutions, we have electrolytes. We have what? Electrolytes. And we have actually two types of electrolytes we are going to talk about. We are going to talk about the weak electrolyte and the strong electrolyte. So a weak electrolyte, who can define for us the term weak electrolyte? Yeah, thank you. A weak electrolyte is an electrolyte which partially dissociates in a solution. Then a strong electrolyte are those substances which fully dissociate or fully ionize in solutions. So we cannot talk about conductivity without talking about electrolyte and conductors. So as we have discussed about these electrolytes, as I've told you, we are going to divide them into types. We are going to talk about the strong electrolyte, and we shall also somewhere talk about the weak electrolyte. So as we have said from our examples, who can give us examples of strong electrolytes? Yeah. Sodium hydroxide. Another one, potassium hydroxide. Even our strong acids, yeah, and others. Then examples of weak electrolytes we have. Who can give us examples? Yeah, we have ethanoic acid and other organic acids. We can also have ammonia solution. Ammonia. These compounds can conduct electricity both in especially aqueous or in molten state. So what do we mean by something being a strong electrolyte? Strong electrolyte. A strong electrolyte will fully ionize. Like for example here, we represent it with an equation. And this arrow shows full dissociation. Then a weak electrolyte electrolyte. Like for example, let's take an example of ethanoic acid will partially dissociate in a solution, which is normally water. So that's a simple difference. So if something is a non-electrolyte, meaning it does not conduct electricity. So similarly to conductor, somewhere we shall be talking about the word conductor. Who can define for us a conductor? Yeah. A conductor is any substance that allows passage of electricity. So all electrolytes, we can call them conductors because they allow passage of electricity through them. Then non-conductors do not allow flow of electricity. That is from physics. So in this topic, we basically deal with two terms, as you've seen in our lesson objective. So we're going to talk about conductivity and the conductance. So conductance of a material or solution is a property of materials due to which material allow flow of ions or electrons through itself and thus conduct what? Electricity. Or we can say that the conductance is the measure of the ease through which current flows through a conductor. This time in chemistry, our conductors are going to be electrolytes. So that's why sometimes we can say conductance is of electrolytic conductance is the conductance of electricity by ions in a solution. So we have a mathematical definition of conductance. We can say conductance is a reciprocal of resistance. Reciprocal of what? Resistance. So here, we are going to say that our conductance G, we are going to use the letter G, is the reciprocal of what? Resistance. And this resistance, you know, resistance from physics is, we said resistance from Ohm's law, we can say V is equal to I what? IR. Where I is current and R is resistance. This time this is also our resistance. Then V is voltage. Normally the units of R who can tell us? Yeah, ohms. You can say ohm or what? Or that one. Oh. So meaning the units of G of our conductance will be per ohm. Or we shall have Those are units of G. Then we are also going to define conductivity or specific conductivity in terms of its mathematical definition. We are going to give conductivity letter K, or we call it kappa, which is equal to the reciprocal of what we are going to call resistivity. So this one here, we call it what? Resistivity. So in our next discussion, we are going to look at the relationship between G and K. So we are going to consider a conductivity cell. For example, that one you can see on your screen. Yeah, we are going to say that if an electrolyte is placed between those two plates, as you can see on your screen, we are going to say that the resistance of that electrolyte between the solution is directly proportional to the distance between the electrodes and inversely proportional to the cross-sectional area. So if we remove that proportionality, we are going to put the term resistivity again. So it has come again. But remember, we want to derive the relationship. We want to relate want to relate our conductance and the conductivity. Conductance and the conductivity. So you'll observe that from what we have written here, we also have, we can say that, we can, let's say this one is our star 1, and this one is our star 2. So using star 1 and star 2, let's call this one star, actually, let's call this one star 2, and this one will become star 3. Yeah. So we want to relate, we want to derive the relationship between these two. So we are going to say that if we relate this one to this one, we are going to say that G is equal to the inverse of resistance. So we shall have this A, which is our cross-sectional area, over resistivity and the times the distance between the plates. So we have got another equation now. We have got another what? Equation. We can call it equation 4. Equation 4. But remember we said but. But our conductivity is equal to 1 over resistivity. 1 over what? Resistivity. So we can say that using this star here, that equation, we can make resistivity the subject of our formula. So we say resistivity is equal to A over GL. Conductance times the distance between the plates. Times the distance between the plates. So hope you are following. So we have now this one. But remember we said also, but as we said here, we are going to say, if we substitute this one in this one, so our K will equal to, so we because this time it is 1 over resistivity, we are going to inverse this one. So we shall have G, which is our conductance, times L, the distance between the plates, and A, which is the cross-sectional area of the conducting plates. So that's what we have. So we have a definition for conductivity. But this equation here is relating conductivity, kappa, which is K, and conductance, G. So from this equation, we can get the mathematical definition of conductivity. So we can say conductivity conductivity is the conductance of a solution. Our solution placed between plates. Placed between plates of 1 centimeter apart and of cross-sectional area of 1 centimeter squared. Yeah. So if this is 1 and this is one, meaning conductivity is the conductance of the solution or of our electrolyte. Placed between plates of 1 centimeter apart and the of cross-sectional area 1 centimeter squared. Yeah, 1 centimeter squared. So we can get the units. We can get the what? Units. Units of K. So how can we get the units of K? So units, we know that this one is per ohm. Can you say like this, per what? Per ohm. Then centimeter divided by centimeter what? Squared. So we are using distance as centimeter, but we can also use meter. So we can say per ohm, per what? Centimeter. Or we can say per ohm, per meter. Or we can say, instead of saying per ohm, we can use Siemens, centimeter per centimeter, or Siemens per what? Per meter. Oh, these are units of conductivity. Units of what? Conductivity. Yeah. So you can, if you look at your screen, you have the definition of conductivity. So differences between conductance and conductivity. So who can give us the differences? So from our definitions, we can know that actually conductance is a reciprocal of resistance, and the conductivity is a reciprocal of resistivity. Then we are going to see that actually conductance depends on the dimensions of a conductor, and the conductivity does not depend on the dimensions of the what? Conductor. Who can give us more differences? Obviously the letters and very many other differences. So now we're going to see how we can measure this conductivity of solutions. Conductivity of solutions. So if you look at your screen very well, you'll observe that we have our diagram here. These are our plates. So the cross-section area of these plates, which is conducting, is what we call A, and the distance between these plates is what we call what? L. Or we can call it D. We can call it what? D. So what we do, we get our conductivity, we get our electrolyte we want to measure its conductivity, and we place it in this cell. So what we always know, how to be able to know the resistance, we should be able to know the resistance between the plates. We can use this Ohm's law by knowing the voltage you are using, the current, then you can be able to calculate the resistance. Then obviously others are measurements like cross-section area, which you can measure, and they are known, and the distance between the plates. Then you say that our conductivity will equal to GL over what? A. But G is the same as reciprocal of what? Resistance. So we can say G resistance A. So after calculating your resistance from here, you can easily get your conductivity. You can calculate your what? Conductivity. So we always encourage you to use alternating current, because direct current normally causes electrolysis. So let's continue very quickly. So because we have known how to determine conductivity, so we can be able to calculate. We can be able to what? To calculate the different questions about this topic. So, for example, using the same conductivity cell, the resistance of 0.1 molar potassium chloride solution and 0.1 molar bromoethanoic acid were found to be 24 and 66.5. The conductivity of potassium chloride is that one. Is 0.01164 per ohm per centimeter. Then the first question is telling us to calculate the cell constant. So what do we call a cell constant? What do we call a cell what? Constant. So cell constant, if you look at our notes very well, just look at your screen. Cell constant is here. The cell constant is actually the L over A. That is the distance between the plates divided by cross-sectional what? Area. So in our question here, they're asking that distance, that cell constant. So we have A. So cell constant, cell what? Constant will equal to L over what? A. L over A. So, but we can get L over A from this thing here, because we have looked at this expression as an application which can help us to measure conductivity. So we can borrow it and use it in our question. So we have our formula. We have written very many, but as we are calculating, we use some of them. So this will equal to K R, which is equal to L over A. So meaning our cell constant, this is our cell constant. Cell what? Constant. So meaning cell constant will equal to, hope you are following, will equal to L over A, which is equal to K times what? R. And what is K? K is conductivity. And if you look at our question, they have given us the conductivity of potassium chloride. We have the conductivity of potassium chloride. We also have the conductivity, the resistance of between the plates using potassium what? Chloride. So what we are going to do, we are going to just multiply here, and we say that we are going to say conductivity for potassium chloride times the resistance of potassium what? Chloride. So we shall have 0.01164 times the resistance, which is actually 24.6. So we have the cell constant. We have got it. We have got you. So here we are going to say 0.11. You can use your calculator. If you've forgotten your calculator, next time come with it. So times 24.6. So our answer will be 0.2863. Can write 4 like that. So because it is L over A, so we shall have per what? Per centimeter. Then we go to part B of our question. Part B of our question, they're asking the electrolytic conductivity of bromoethanoic acid. Bromoethanoic acid. So this time they want us to get K, which is our electrolytic what? Conductivity will equal to this. You can say our cell constant times 1 over R. So our cell constant is 0.286344 times 1 over the resistance caused by bromoethanoic acid, which is 66.5. Yeah, 66.5. So you can divide your answer by 66.5. And we shall get a beautiful answer here, which is 4.3059 times 10 to the power negative 3. Negative what? 3. What are units per ohm? per centimeter. Those are units of what? K. Yeah. So we are going to look at another example. Another what? Example in our exercise. Yeah. So this exercise, we have 2 questions. Actually, we have 3. We even have this one. We are going to do one of them. But if you look at this one, the first question says the cell resistance containing 0.1 molar of sodium chloride solution is 50.62. In the cell of 0.02 molar potassium nitrate has a resistance of 185 ohms. Yeah. If the conductivity of sodium chloride is that one, then calculate the cell constant. So you can do the same thing because they have given the data about sodium chloride. Then using the resistance after getting the cell constant, because they are using the same cell. If they are using the same cell, it means that the cell constant will remain the what? The same. So you calculate again cell constant times 1 over R. Then we have another question here which says the resistance of a decinormal solution of a salt occupying a volume between 2 electrodes, platinum electrodes, that is 1.8 centimeter apart and 5.4 centimeters squared in area. So they have given us the L and the A, was found to be that one. Then they are telling you to calculate the electrolytic what? Conductivity. So it is easy. How easy it is? Because they have given you L, they have given you what? A, and they have given you what? R. What you need to do is to substitute. I know you do that one. Then we have another example also. Have another what? Example. Or we can call it this as our exercise. Make sure you do these numbers. Let's first leave it for some time. Then you copy it very well, or you can take a screenshot. Yes. Yeah. Okay, so number 3. A conductivity cell was filled with 0.01 potassium chloride, which was known to have a specific conductivity. So you try out this question. Yeah, I think it's the same as the other one. Get the cell constant, get the specific conductance. Thank you very much for following me. Hope you followed. And make sure you try out the questions you have left. God bless you very much. See you next time.